Yet we can see its effects every day, and without it, life couldn't survive. So what is energy? Where does it come from? And how can we produce the energy we need? These reasonable and straightforward questions can be surprisingly difficult to answer. We might start by thinking of energy as what we get when we use fuels, things like coal, oil or gas. We've all seen the effects of using these fuels to heat our homes or power a car, train or aeroplane. In some way, we've released the energy stored in these substances so that it can do useful work. We measure energy in units called joules. If you pulled a brick to the top of a house using a pulley, you'd have transferred about 50 joules of energy from your body to the brick. This energy can be transferred again if we let the brick fall into a bucket of water. Some of it's transferred to the water as it splashes out of the bucket, and the rest increases the temperature of the water ever so slightly. After all this activity, every joule of energy can be accounted for. Energy is never used up, even though the fuel which provided it might be. In reality, the energy transferred to the brick and then to the water is transferred in turn to the air and to the ground. Here it can't do any more useful work, and we might think of it as lost. But where does energy come from? Unfortunately, this isn't a simple question, and we still don't have a definite answer. The best suggestion is that it was the result of the formation of the universe 15,000 million years ago. As far as the Earth is concerned, the question is more straightforward. All the energy we use comes directly or indirectly from four main sources: the sun, the interior of the Earth, the movement of the moon, or the atom. We'll look at each of these sources and how we use them. The sun radiates energy at an incredible rate as a result of the nuclear reactions taking place within it. The Earth's outer atmosphere receives about the same amount of energy from the sun each minute as the entire population of the planet uses in 2 weeks. Unfortunately, much of this energy doesn't reach us. A lot gets reflected back from the surface, or reflected and absorbed by the clouds and dust in the atmosphere. And what does reach us is in a low-grade form, harder to use than other energy sources which can generate higher temperatures. Nevertheless, solar energy is vital to our survival. If the sun suddenly stopped shining, the Earth would begin to cool, and the entire world's stocks of fuels couldn't delay this for more than a few minutes. All life, and not just life as we know it, would come to an end. On average, each square metre of the Earth's surface receives 1,400 joules every second. This isn't evenly distributed across the planet because of the Earth's shape and the tilt of the axis. As a result, areas close to the equator can make the best use of direct solar energy. This direct solar energy is important both to provide heat and, through solar cells, electricity. Even in Europe, the contribution which solar energy can make to our overall energy needs shouldn't be underestimated, especially in the sunny south. But even in the north, modern building design has taken advantage of solar heating, producing energy-efficient houses, like these at Milton Keynes, designed both to keep the heat in and to exploit what sunshine there may be to heat them up. The sun also provides important energy sources indirectly. Solar energy heats the Earth's atmosphere, but this heating isn't even. This produces differences in air pressure, which in turn cause air movements or winds. This moving air has kinetic energy, some of which can be extracted by windmills. There's nothing new about this technology. Windmills like these have been common in Europe for more than 300 years. Traditionally, energy extracted from the wind has been used for mechanical tasks: grinding corn, pumping water, sawing wood. Windy, flat lands like East Anglia and the Low Countries, Belgium and the Netherlands, have always had windmills. Now there are some new designs, driving turbines to generate electricity. These are at the harbour mouth of Zeebrugge, and there are more in Norfolk. They're often grouped together to provide wind farms, capable of generating enough electricity to supply several thousand homes. Although wind farms are able to generate electricity without polluting the environment, they can be unsightly, and they're dependent on the weather, of course. As well as producing winds, the sun's energy drives the water cycle, evaporating water from lakes, rivers and oceans and depositing it on high ground. The energy of this water is released as it falls back to the ocean and can be used to turn electricity-generating turbines in hydroelectric power stations. This one's in Derbyshire. The turbine is the key feature of electricity generation. Something, like water in a hydroelectric plant, drives the turbine blades and turns the generator which produces electricity. We shall see turbines at the heart of all electricity generating schemes. Hydroelectricity supplies about a quarter of the world's electrical power, but its importance depends on location. Many schemes require very large dams for their vast turbine halls, and these have an enormous impact on the environment. In addition, a reliable and substantial rainfall is needed, so this method of electricity generation is not suitable for many countries. Another method of extracting indirect solar energy is from waves produced by the action of wind on large expanses of water. The energy contained in waves can be very large indeed. Waves can erode cliffs, change coastlines, and move millions of tons of sand and shingle. Energy can be extracted from waves by using turbines again. Several different designs have been tried, some using columns of air driven by the waves, others using the water itself. The technology for extracting energy from waves is still under development, and as a result, wave energy makes no real contribution to world energy demand at present. For millions of years, plants have been storing energy from the sun in chemicals. In turn, animals, including ourselves, have eaten the plants to obtain energy. Plants high in carbohydrates, such as grains, sugarcane and sugar beet, are valuable food crops. This sort of plant material can also be fermented to produce alcohol, which in turn may be used as a fuel. In Brazil, they've been running cars on this for years. Other plant material, like peat, straw or wood, may be burned, releasing energy for heating or cooking. These are all simple examples of biofuels. There's increasing interest in using biofuels for electricity generation. In this case, a power station in Suffolk, it's not directly plant material that's being used, it's animal waste, chicken droppings. The droppings and the litter from the chicken houses and farms in the surrounding countryside are collected here to be burnt at a high temperature. It's brand new technology. The heat of the furnace turns water into steam in the power station's boilers, and the steam drives turbines generating power for the national grid. This sort of power station is unlikely to have a major impact on electricity generation in the near future, although it may be an efficient way of dealing with the increasing amount of refuse the developed world produces. Other sources of stored solar energy may be rather more familiar. Coal, oil and natural gas, the so-called fossil fuels, are all products of once living organisms. Coal is a black mineral containing a high proportion of carbon. It was formed from the remains of swampy forests which spread over large areas of the land around 300 million years ago. Coal deposits are widespread and large reserves remain unmined. Coal may be burned to provide energy for heating and cooking, but large amounts are used by industry and for producing steam to drive turbines in electricity generation. This is not a very efficient method of producing electricity. In addition, coal contains sulfur impurities, which when burned contribute to acid rain. And like all fossil fuels, it produces carbon dioxide, a greenhouse gas. The remains of tiny aquatic plants and animals are responsible for the formation of oil and gas. Both contain a greater amount of hydrogen combined with carbon than coal. They also have the advantage that they can be easily transported by pipeline rather than by lorry or rail. Deposits of oil and gas are dependent on particular geological features to trap them. They don't occur as widely as coal. Energy is produced by burning these fuels and producing steam to power turbines. Like coal, oil may contain sulfur compounds and contribute to acid rain. Oil also produces petrol, diesel, kerosene and fuel oils. These are vital for our transport system, and without them we'd find travel very restricted. Oil is also important because of the chemicals it contains. They form valuable starting materials for the chemical industry. Without them, we'd have no man-made fibres or plastics. The interior of the Earth is still hot. Some of this geothermal energy may be extracted by pumping cold water down to these heated rocks and using the hot water which returns to the surface. Or you may just need to pump up hot water that's down there already. One such scheme is in operation in Southampton. The hot water is pumped up in a car park in the centre of the town. Inside the plant, the water arrives at a temperature of 74 degrees Celsius. Not hot enough in this case to produce steam and drive a generator, but hot enough for central heating. The brine pumped up from the ground passes through a heat exchanger to pass on its heat to fresh water. Then the brine's allowed to run away. The heated fresh water is pumped out of the plant to heat parts of the city of Southampton. Many of the buildings around the geothermal station are heated with the water from the plant. A few countries now are using this form of energy, but it's still relatively underdeveloped. The other sources of energy, in addition to the sun and the earth itself, are the moon and the atom. The gravitational attraction of the moon as it orbits the earth causes 2 high tides and 2 low tides of the oceans each day. The tidal movement of water has been exploited for centuries in tidal mills to do the same sort of things as traditional windmills, like grinding corn. This old tidal mill is in Hampshire, but a number of modern plans have been devised to use the water flow produced by tides to turn turbines and generate electricity. At present, one of the most successful is on the Rance estuary in Brittany. The height of the spring and autumn tides here can reach the exceptional figure of 13.5 metres. There's a huge volume of water, 180 million cubic metres, which can be used to drive the turbines in the turbine hall, deep below the top of the barrage. So large is the barrage that the engineers use bicycles to get about down below. The barrage generates as much electricity as a medium-sized conventional power station. But, like dams, barrages such as this can have a dramatic effect on the environment, and their application is limited. The final source of useful energy available to us could not have been imagined 100 years ago. Yet today, nuclear energy and its effects are part of public debate. In fact, there are two different energy-releasing processes which can take place in the nuclei of atoms. In the first of these, nuclear fission, atoms of a type of uranium are split apart. This releases energy in the form of heat and fast-moving neutrons. These neutrons collide with more uranium atoms, causing them to split. This chain reaction continues unless the neutrons are absorbed or the uranium is used up. The heat released by nuclear fission can be used to generate steam, which can turn turbines in the same way as in a coal or oil-burning power station. There's nothing mysterious about nuclear power. It's just another way of heating water to get steam to drive a turbine. These pictures were taken at Sizewell in Suffolk while the turbine hall was under construction. As well as energy in neutrons, the splitting of uranium forms highly radioactive waste material. Although uranium is a rich energy source, the safe storage of the radioactive waste products is vital to the use of this form of energy. About 10% of the world's electricity is generated by nuclear power. In some countries, such as France and Switzerland, more than 40% of the electricity is produced in this way. There's a second possible nuclear energy source which may allow us to stop using up the world's valuable raw materials. Nuclear fusion, in which the nuclei of two small atoms are fused together, and this also releases energy. It's the same process which has kept the sun shining for thousands of millions of years. The main fuels for this process are forms of hydrogen with different numbers of neutrons in their nuclei. They're called isotopes and are found naturally combined with oxygen in water. At present, no one's produced a viable power plant using nuclear fusion. One reason for this is the extremely high temperatures involved. But if the problems of containing the reaction can be solved, fusion could be an extremely valuable source of energy in the 21st century.